Vinny, Tony, get a load of these bozos, huh? Bunch of wise guys, huh? They think they can do this integration stuff? Huh. They're gonna be sleeping with the fishes. Oh, sorry guys, hey. I wasn't talking to, I wasn't talking to, Tony's. I was talking to just some students over there. You know, I'm not part of the mafia. Okay, do not send the feds after me. Okay, this is just my 20s gangster outfit for Decades Day. It is Spirit Day, and it was a heck of a day. So to end the day, I'm gonna do a little bit of another integration rule here. We have what we call the reverse chain rule. So with integration, we've learned that that is the opposite of taking a derivative. And if we can do the reverse power rule, then, well, there must be a reverse chain rule, and, well, that's what we're going to talk about today. It might be helpful to actually recall what the chain rule is when it comes to derivatives. If I have the derivative of some function g of x within an outer function f of x, well, the derivative of that will be f prime of g of x times g prime of x. But we weren't calling it g of x, right? We called it u. We set u equal to g of x. And so, really, if we're doing the derivative of f of u, you get f prime of u times u prime. And this is our chain rule right here. So the derivative of the outer function with the original inner function inside, multiplied by the inner function's derivative. So we have a couple examples here that we're going to take a look at. We're going to see how the chain rule works once again, and then we're going to try and work backwards and see if we can use some kind of method. The method is called U-Substitution, and you'll see why in a second. All right. So let's start with A of these three functions. So with A, what I'd like to do is I'd like to determine what my outer function is and what my inner function is. So my outer function was something raised to the fourth power, so x to the fourth power. U, my inner function, is x minus 2. So now I'm going to take the derivative of both of those. F prime of x is 4x to the third. U prime is just 1, right? Just taking the derivative of this guy, the constant goes to 0. Putting this all together, f prime of u, well, I have my f prime as 4x cubed, and my original u function, x minus 2, is going to go in for x right here. So I get 4 times x minus 2 to the third power times u prime, which is just 1, which doesn't change our answer that much. So we get 4 times x minus 2 to the third power, and that's the derivative of this guy right here. Okay? Again, let's see it with B and C again. Again, just kind of getting this practice under our belt and getting review, because we didn't go over it extensively, but we did touch on it, and now we're going to kind of need to use it again. Okay? So 2x plus 5 to the 7th power. Again, I identified my outer function as x to the 7th, took the derivative of that guy. My inner function was 2x plus 5, took the derivative of that. And so now, kind of putting it all together, I'm taking my f prime, and I'm plugging in my u function into x, right? So I get 7 times 2x plus 5 to the 6th times u prime, which is 2. And putting that all together, I get this as my derivative of this original curve right here. And finally, let's look at something like this guy. If we have an exponent in the denominator, it's a good idea to write it up in the numerator with a negative exponent. Easier to do derivatives of that. Again, I identified my outer function as x to the negative third, and then I recognized that my inner function was 2x minus 1. Okay? Putting that all together, I end up getting a derivative of negative 6 over 2x minus 1 to the negative fourth power, but of course if it's negative, I can just put it back in the denominator, and it makes it a positive exponent again. Alright, that's the chain rule with derivatives. So now we kind of want to find or look at a method that actually helps us work backwards. Okay? So what I want us to do is using these three answers that we got from our derivatives, can we work backwards and go from our derivative back to our original curve? We should be able to if integration is in fact the opposite of derivatives. So this is where we enter something called U-Substitution. And there's really 5 steps to it, okay? And we'll go faster as we go, but I really want to break this guy down. So the first one, letter A, we're going to integrate this function right here. That's what I got integrated right now. All right. Well, I got really 2 distinct pieces going on. Again, it kind of looks like there's an outside function and an inner function. So what we do, because it's called U-Substitution, is I set my u equal to the inside function. In this case, it's x minus 2. And it's clear to me it's x minus 2 because it's in parentheses. So I find what that is. And then I need to take the derivative of u, right? So I take the derivative of both sides. And when I do this, I have to include my dx next to this derivative over here, okay? That might not be so obvious right now. Don't worry about it, okay? You need your dx, though, because if you look up here, even though I'm doing u equals x minus 2, and that's going to be my u, I can't integrate with respect to dx. I have to do it with respect to du, right? So I need to actually solve for my dx. And this one's really not that bad, right? You divide both sides by 1, and so du equals dx. There's really not a whole lot we can do right there. Now, what I'm going to do, this is probably the most extensive part. We're going to replace the inside function with u, officially. And then we're going to replace dx with our du term, which is this guy. This du over 1 is our du term. So, taking a look at that, I take this curve, right? And so now x minus 2 is really u now. And dx is now du over 1, and really that doesn't change what we got. So we're now going to be taking the integral of something a lot easier to take the integral of, which is just 4u to the third power. And we know how to do that because we know the power rule. So now we're going to integrate the function with respect to u. And what I'm going to do is I'm going to pull out this 4 because really it's a constant and it's just going to multiply anyway by whatever I integrate here. I take the integral of u to the third, and I get 1/4 u to the fourth, and I have to remember to multiply by that 4. So these guys are reciprocals, they cancel out to 1, and so I get u to the fourth plus c, right? I can't forget my plus c. This is an indefinite integral, there are no bounds. So I include my plus c, but this wasn't exactly what I wanted to keep, because remember, we were trying to find the derivative of this guy, right? And so instead of u, now I'm going to replace it with x minus 2. And so I have x minus 2 to the fourth power plus c. And if we look back to our original curve that we started with, that's what we had. X minus 2 to the fourth power. X minus 2 to the fourth power plus c, right? We learned that with indefinite integrals, we need to include that because we don't know what the constant is. In this case, it's 0. But again, we don't know that if we were just not given this information, right? So that guy worked out. And in fact, you could use this for all of these. This is the reverse chain rule right here. Okay, this process can be used to solve integrals that have functions that are within each other. Okay, let's see another example. Let's look at letter B. Whoa, spoiler alert. Let's look at letter B. All right. Again, kind of starting with this guy, and our goal is to really get back to what we had to begin with. This guy, 2x plus 5 to the 7th. That's our goal, right? So again, I'm going to set u equal to my inside function, 2x plus 5. And then I need to take the derivative of that, so I get du equals, the derivative of this side is just 2 dx. I need to include dx on the right side when I do this, because again, I need to figure out what dx is for step 3. Dx is equal to du divided by 2 this time. Now this kind of matters a little bit more, and you'll see what happens. Okay. So step 4 is actually replacing my inside function with u and replacing dx with our du term. In this case, my u just goes in here. And my du was over 2, so I'm dividing this whole thing by 2, which means this guy, this 14, reduces to 7. Okay, so I have to integrate 7u to the 6. Again, a much easier integral to evaluate, or not to evaluate, a much easier integral to achieve, compared to something like this, right? And we could do that a lot in math. We can write something in a way that makes more sense to us, and that's really what I like to think U-substitution is. Writing it in a way where it's easier for us to comprehend, okay? So again, I pull the 7 out. I'm going to end up multiplying by 1/7 u to the 7th, so I get u7 plus c, because it's indefinite. I replace u with my 2x plus 5, and yeah, that's what that was our goal. We were trying to get back to that, and we did. Ha! Nice job. All right. What I'd like you guys to do, I encourage you to do it, is pause the video and try this guy. I rewrote it for you. Okay. I just took this guy and I moved it back up in the numerator. Much easier to integrate. So give it a try and go for it. All right. And go. All right. Let's see what we came up with. Here are the steps. Step 1, u equals 2x minus 1. That was our inside part to this guy, right? So u is equal to 2x minus 1. Then I do du equals 2 dx. Take the derivative of this side, include my dx. Solve for dx. I get the same thing I did for letter b. And now I'm going to replace this inside function with u. And I'm going to replace dx with my du term, du over 2. So negative 6 and 2 reduce to negative 3, u to the negative 4th. We're integrating that with respect to u. I pull the negative 3 out, and we integrate. We are working with a negative exponent, so be careful with that. That's probably where you are more than likely going to trip up. But we do 1 over negative 4 plus 1, so we get 1 over negative 3 multiplied by negative 3. Cancels out to 1, which is nice. And so I just have u to the negative 3rd plus c. Replace u with 2x minus 1, and then I throw it back in the denominator, and this is the original curve that we get back. And that is all good and dandy, because that is actually what we started with this guy, kind of going backwards, right? So again, giving you more faith in this reverse differentiation, understanding that integral is in fact the opposite of a derivative, but also showing you kind of an interesting way of doing going backwards. Okay, this process right here. The book does it differently. They give you a formula. If you find the formula useful, by all means use it. I just think this is more intuitive, and it makes sense because, well, if we learn the chain rule as changing g of x to u, kind of makes sense. We change our inner function to u as well, right? So again, kind of a little bit more intuitive with how we've been learning chain rule. This is Mr. Knight, signing out. Have a good day. This isn't real, by the way. This is fake, so it's okay.